Welcome to this Finals Prep Explainer. Today, we're taking all that data center engineering theory you've been learning and turning it into applied practice. If you've been keeping up with the material, you already know the basic concepts. So, we're shifting gears. We're focusing heavily on math, analytical thinking, and scenario-based problem solving. Think of this as your ultimate study guide. We're going to break down complex questions and walk through the solutions step by step, so you walk into that final exam completely prepared. We've got 5 targeted blocks today to get you ready. Core design and tiers, redundancy capacity planning, efficiency math, density retrofits, and finally, Bangladesh site constraints. Let's get to it. All right, Section 1, Core Design and Tiers. Let's talk about the Uptime Institute tiers. This tier data brilliantly shows the literal exponential cost of reliability. I mean, look at Tier 1. It gives you 99.671% uptime. Sounds pretty good, right? Well, until you realize that actually allows for almost 29 hours of downtime every single year. But then, check out Tier 4, 99.995% uptime. We're talking just 26 minutes of downtime for the entire year. No way around it. Getting there means shifting your redundancy from a basic N setup all the way to 2N. And just a heads up, every step up this ladder is going to add roughly 20 to 50% in your capital and operating costs. So here's a classic analytical question you should absolutely expect to see on your exam. What is the key distinguishing feature that separates a Tier 3 data center from a Tier 2 facility? Seriously, pause this explainer for a second and really think about it. What actually justifies that massive leap in cost between Tier 2 and Tier 3? The crucial answer here is concurrent maintainability. Now, don't fall for the trap of thinking it's just about, slapping in a few extra generators or having some spare parts laying around. Tier 2 already has those extra parts. Tier 3 actually means you can shut down any single active distribution path for planned maintenance, and it has absolutely zero impact on IT operations. It's a fundamental architectural property of the building itself, not just a simple hardware count. Moving right along to Section 2, Redundancy Capacity Planning. Let's unpack these capacity models. So how exactly do we plan for those backups? It all starts with one letter, N. N is the bare minimum number of units required to meet your IT load. Honestly, understanding N is the absolutely crucial point for capacity planning because everything else, whether we're talking N+1 or 2N, is simply a mathematical expression of your spare capacity mapped right back to this baseline. If your N is broken, the whole facility goes dark. Time for a scenario question. Let's say a cooling system needs exactly 3 chillers to meet the full load, but 4 are actually installed. If you need 3 but you buy 4, what redundancy model are you actually building here? Let's break down the step-by-step solution. Step 1, identify your required capacity, which means N equals 3. Step 2, identify the total installed units, which the scenario tells us is 4. Step 3, just calculate the difference. 4 minus 3 equals 1 spare unit. By stepping through that logic, it's pretty clear we're looking at an N+1 model. And by the way, that is the most common commercial standard for Tier 2 and Tier 3 facilities. Having that 1 spare allows a single unit to fail or go offline for maintenance, while the remaining 3 seamlessly carry the whole load. Here's another quick concepts check before we move on. Why does 2N redundancy cost substantially more to build than an N+1 design? Take a second to visualize the physical infrastructure needed for full duplication versus just adding a single spare. If you guess you have to buy twice as much stuff, you hit the nail on the head. 2N isn't just buying 1 extra unit to sit in the corner. You're literally building a completely independent, parallel facility within the same walls. You duplicate the entire capacity and the entire distribution path, end to end. This roughly doubles your capital costs. That is exactly why it's strictly reserved for Tier 4 critical infrastructure where failure is, frankly, just not an option. All right, grab your calculators for Section 3, Efficiency Math. Let's dive into PUE calculations. The absolute defining metric for the industry is PUE, or Power Usage Effectiveness. It's calculated by simply dividing the total facility power by the IT equipment power. The really interesting thing about this formula is the ratio it creates. The closer your PUE is to 1.0, the less power you're wasting on overhead like cooling, distribution, and lighting. Now, a PUE of exactly 1.0 would mean 100% of your power goes straight into computing. That's physically impossible in the real world, but it's the holy grail we engineer towards. Before we get to our math quiz, I want you to memorize this massive number, 94.6. That's 94.6 minutes, and it is the absolute maximum allowable downtime per year for a Tier 3 facility to maintain its 99.982% uptime promise. It's a fantastic analytical data point to drop into short answer questions to prove you really understand the real-world implications of those uptime percentages. Okay, time to practice. Here's your scenario. A facility has an IT load of 750 kilowatts and a total facility power draw of 1,050 kilowatts. What is its PUE? Grab some scratch paper, pause the explainer, and just run this quick one-step calculation. Let's break down the math. Step 1, our total facility power is 1,050 kilowatts. Step 2, our IT equipment power is 750 kilowatts. Step 3, we simply divide 1,050 by 750, giving us a PUE of 1.4. So following those steps, a PUE of 1.4 means that for every single kilowatt of actual computing power, you're spending 0.4 kilowatts on cooling and infrastructure overhead. Just for context, anything under 1.5 is generally considered quite good in the industry today. Moving into some applied engineering now. Section 4, density retrofits. We're looking at greenfield versus brownfield.
When you're comparing builds, greenfield obviously offers full design freedom because you're starting with empty land. But it takes about 18 to 24 months to construct. Brownfield retrofits, on the other hand, are much faster, typically 3 to 9 months, but they carry a really high risk of live downtime. When you're weighing new builds versus retrofits, the deciding factor almost always comes down to how quickly you need the capacity versus how much risk you can tolerate working around live, critical systems.
Consider this very modern, real-world scenario. A facility needs to raise its rack density from 5 kilowatts all the way to 25 kilowatts to support new GPU servers. What is the most practical redesign approach without a full rebuild? Think critically here. If you can't just tear down the whole building and start over, how in the world do you manage a massive 5x jump in heat for just a handful of racks? This is where modern problem-solving shines. The answer is a targeted density redesign. You avoid the full facility rebuild entirely. Instead, you create specific high-density zones right there on the floor. You install rear-door heat exchangers and deploy direct liquid cooling to those specific racks. This strategy isolates the GPUs and handles the heat right at the source, without disturbing the standard airflow for the rest of the facility. And for our final study block, Section 5, Bangladesh sites. Let's look at local constraints. Analyzing the local engineering realities in Bangladesh reveals several unique constraints. First, the region has a high vulnerability to monsoon floods. Second, grid voltage fluctuations mandate extremely robust generator backups. On top of that, the Bangladesh Bank is actively driving Tier 3 standards for compliance. And because of high urban density, retrofits heavily dominate over new greenfield builds. Look, in Bangladesh, grid instability means those N+1 diesel generators aren't just backups sitting there for an emergency. They are everyday necessities, which obviously drives up both your capital costs and environmental emissions. All right, here is your final scenario-based question to put everything we've learned together. A bank wants to build a new data center right near the Budiganga River for cheap land and really easy access to cooling water. What is your very first architectural objection? Put on your site assessor hat for a second. Why might cheap riverside land actually be a catastrophic engineering choice in this specific region? The answer? Flood risk heavily outweighs water access. Inundation risk is the absolute deal breaker here. You absolutely must prioritize drainage and elevation above all else. You just do not compromise the safety of a Tier 3 facility just to score some cheap water cooling. Instead, the right move is to build on elevated land and solve the cooling problem using closed-loop systems. And that brings us to the end of our finals prep. But I want to leave you with this. As AI pushes density beyond 100 kilowatts per rack, will future data centers be built near the cities that actually need them, or solely where nature and power grids dictate? Keep that provocative thought in mind as you head into your exam. Good luck on your finals, keep practicing those math scenarios, and keep questioning how we build the backbone of the internet.